So if 2 moles of hydrogen ions react with 2 moles of hydroxide ions, the delta H, the enthalpy change will be twice. Now, since energy is given out, this is an external process, and therefore it should carry a negative sign. Enthalpy of neutralization is what we are going to look at today. In our first lesson, we talked about the introduction. We talked about exothermic reactions and endothermic reactions, and I hope everybody is well conversant with such reactions. Then in our second lesson, we talked about enthalpy of combustion, and we described an experiment to determine the enthalpy of combustion of methanol. And I told you that it will not always be methanol, that it can be any other organic or any other liquid which can burn to produce heat energy. It can be propanol, it can be methanol, it can be paraffin, or any other liquid which can burn to produce heat energy. And that method can be used to determine its enthalpy of combustion. The method which we describe applies to substances which are in liquid form. In today's lesson, we are going to talk about enthalpy of neutralization. When you look at this word neutralization, is something to do with neutral. In this case, a substance which has been acidic reacts with another which is alkaline, and the product is neutral. So a neutral product is formed. That's why that process is called neutralization. A neutralization reaction occurs between an acid and a base or an alkali to form a salt and water only. In our enthalpy of neutralization definition, this is what we have. It is the enthalpy change occurs when 1 mole of aqueous hydrogen ions reacts with 1 mole of aqueous hydroxide ions to form 1 mole of water. So just as you see the equation, this is 1 mole, this is 1 mole, and even this is 1 mole. Whenever 1 mole of hydrogen ions reacts with 1 mole of hydroxide ions, 1 mole of water is produced, and this is the energy which is given out, and it is 53.7 kilojoules for every mole of hydrogen ions reacting with a mole of what? Of hydroxide ions. So that's the equation of the neutralization reaction. We must emphasize that this word one should be a word one, not a number one. And also we emphasize that word 1 mole, the phrase 1 mole is used 3 times in this definition. So we don't need to forget that. Then it is wrong to define this as it is wrong to define this enthalpy change as one which occurs when 1 mole of an acid reacts with 1 mole of a base or an alkali. It's wrong to define enthalpy of neutralization as the enthalpy change occurs when 1 mole of an acid. Why? Because not all acids are monobasic. We have only a few acids which are monobasic, and some acids are dibasic, and others are tribasic. So, for example, if you are dealing with the sulfuric acid, 1 mole of sulfuric acid means 2 moles of hydrogen ions. So this definition cannot apply because not all acids are monobasic. The same applies to 1 mole of an alkali. We have alkalis which are in which one molecule has two hydroxide ions, e.g. magnesium hydroxide, magnesium hydroxide, and so on and so forth. So we must define this as a variable. When one mole of hydrogen ions reacts with one mole of hydroxide, but not as the enthalpy change occurs with one mole of an acid, because acids do not have the same basicity. We have those acids which are monobasic, we have the dibasic ones, we also have the tribasic ones such as phosphoric acid. So we shall not be defining it as a method equals one mole of an acid, but instead we shall put our emphasis on the hydrogen ions and the hydroxide ions. We say that this process here need to put an organic solvent which can dissolve this ink. Get rid of it. This process here is the neutralization process. The neutralization is so. Meaning that each energy is given out. So when you mix a solution of an acid with a solution of an alkali, heat energy will be given out, and you can even testify by touching the resultant mixture. If it is in a beaker, for example, you can use your hand to feel. You feel that it becomes warmer. The enthalpy change here has this value. We need to note something. If the reaction occurs between a strong acid and a strong base, then enthalpy of neutralization will be equal to negative 53.3 kilojoules per mole. If the reaction occurs between a strong acid and a strong base, then that's what you will have. Why is it like that? Here is the explanation. The reason why, if a reaction occurs between a strong acid and a strong base, the enthalpy of neutralization is 57.3, is because both a strong acid and a strong base fully dissociate in a solution. Example of a strong acid, we can talk about HCl, hydrochloric acid. Whenever it is dissolved in water, it will fully dissociate these hydrogen ions and the chloride ions. Then another example of a strong base is sodium hydroxide, and whenever it is dissolved in water, it will fully dissociate to give us sodium ions and hydroxide ions. So the hydrogen ions and hydroxide ions will always be readily available to react with one another, because the other substances have readily provided them. They readily provide the hydrogen ions. Why? Because for them, whenever dissolved in water, they will fully dissociate. So when you have 1 mole of hydrogen ions here and 1 mole of hydroxide ions, even if it's a molecule dissolved in water, it will automatically give you the hydrogen ions and the hydroxide ions. And once they are provided, they will eventually react. And since their reaction produces negative 53 kilojoules, 57.3 kilojoules per mole, then that will be the enthalpy change. In the following cases, the enthalpy of neutralization of visualization, we have a smaller i.e. less heat energy in the following cases, the delta H neutralization will have a smaller negative value than this. In other words, less heat energy is given out. The first case is in a reaction between a strong acid and a weak base or weak alkaline. Another case is in a reaction between a weak acid and a strong. And the third case is in a reaction between a weak acid and a weak base. In any of these cases, the enthalpy of neutralization will have a smaller negative value than that. E.g., it can be negative, say negative 50, negative 51, something which is having a lower magnitude than this, maybe negative 50 kilojoules per mole, or negative 49 or negative 55. The values will always be smaller in magnitude than this if you have any of these cases considered. And here is the explanation. solution. It's a weak base. Now these substances, when dissolved in water, they fully weak acids. They partially dissociate weak acids and weak bases only partially dissociate or partially ionize in a clear solution. For example, ethanoic acid being a weak acid, it will only partially dissociate. It's ammonium hydroxide, it will partially dissociate. Now, since they partially dissociate, it means that when you are reacting a strong acid with a weak base, the strong acid will provide all the hydrogen ions in the solution, but the weak base will be struggling to provide the hydroxide ions. That means that the hydroxide ions will not be readily available to react with the other hydrogen ions from the strong acid. So what happens is that the heat energy which has been given out, some of it will be used to convert these unionized or undissociated molecules of the weak base into the ionized molecules. Some of the energy which would have been given out to reach this value is used in dissociating the weak base or the weak acid so that it provides the hydroxide ions. Because at the end of it all, it will have to react fully. But there is a lot of struggle in converting the unionized or undissociated molecules of a weak base or a weak acid into the ions which we are interested in, which have to meet so that the neutralization reaction takes place. So some of that heat energy which would have been liberated in order to reach this value, that energy is used in dissociating the weak acid or a strong base. So if we consider a reaction between a weak acid and a strong base, the strong base will fully dissociate or ionize, it will fully dissociate and will produce the hydroxide ions, ready to react with the hydrogen ions. But the weak acid will be struggling to dissociate or to ionize to produce hydrogen ions. So some of the heat energy which is produced in the first, when the hydroxide ions of the base meet with those hydrogen ions which have been found, some of the energy which would have been liberated will be used in dissociating the weak acid to provide the hydrogen ions. Because at the end of it all, the hydrogen ions will have to be produced so that they react with the hydroxide ions of the strong base. In another scenario where we have a weak acid and a weak base, this is worse, because both of them are struggling. This one has produced very few hydrogen ions and this one has produced very few hydroxide ions. The two will meet. Now that small amount of heat energy that has been liberated will be used to come back and dissociate or ionize these unionized molecules. So a lot of energy will have to be used in ionizing these molecules, and therefore the overall heat energy which is given out to the surroundings will automatically be lower than 57.3. So that question is very common. They ask you to explain why a reaction involving either strong acid, involving either weak acid or weak base will have a smaller enthalpy change than 57.3. The reason is that some of the energy which would have been liberated to the surroundings is used to dissociate the weak acid or weak base, because this dissociation process requires heat energy. So it takes some of that heat energy which would have been needed to which would have been given out. So that's why the value is always very small. We have that explanation in our notes. We are not going to write it again because it's already there in our notes. I'm just trying to explain it. Now we are going to talk about an experiment. To determine the enthalpy of chloric acid so in this case we set up a chemical reaction and then try to measure the amount of it which is given out. So you make a reaction take place using known volumes and known amounts of the acid and the base, and when the reaction occurs, as we have said that the neutralization reaction is exothermic, heat energy will be given out and therefore it will raise the temperature of the resultant solution. So we need to measure that temperature rise and use it to determine the enthalpy as follows. So this is our procedure. We need to measure the volume so we know the volume and even the molarity. So you measure this volume and of course the constant has to be known, then put it in a dry plastic beaker. Why a plastic beaker? Because plastic is a poor conductor of heat. So we are trying to minimize the heat losses that are occurring due to the apparatus used. If you use a metallic beaker or a glass beaker, it can conduct heat more easily than a plastic beaker. So this is the poorest conductor among the common kind of beakers that we can have. This is the poorest among them, so it can maintain our heat. Then using a thermometer, measure and record the temperature initial temperature of the solution. Let's call it T1 degrees Celsius. That's the temperature of the solution of sodium hydroxide. Then you also do, after measuring the temperature, you wash thermometer and dry it, because this is the same thermometer which we are going to use to measure the temperature of the hydrochloric acid. So we need to make sure that it does not contain sodium hydroxide. So after washing and drying the thermometer, then we measure an equal volume V cubic centimeters of 1 molar hydrochloric acid. So this is the same volume and the same molarity. Remember, one molecule of sodium hydroxide produces 1 hydroxide ion, and then 1 molecule of hydrochloric acid produces 1 hydrogen ions. So you have an equal number of moles of hydroxide ions and hydrogen ions. So that can give us a very, very easy calculation. And you record its initial temperature, T2 degrees Celsius, using the same thermometer which has been washed earlier. Which has been washed and dried. We want to use the same thermometer so that we can tell really, we can have the same calibration. You add the hydrochloric acid at once, the sodium hydroxide solution which is already in the plastic beaker. Then carefully stir the mixture using the thermometer. Using the thermometer. So when you add the two, hydrochloric acid and sodium hydroxide, the neutralization reaction will start take place and heat energy will be given off. This heat energy will raise the temperature of the solution, and this will be recorded, or this will be monitored by observing the thermometer. So the temperature will rise. If this is our thermometer, the temperature will rise from our initial value slowly by slowly, because the reaction is producing heat, slowly by slowly, and then it will stop rising. When it stops rising, that means that the reaction is complete, and that's the maximum attainable temperature. And after some time, cooling starts, because this substance is interacting with the environment. So the temperature will start to fall again. But we make sure that we note that temperature, that constant temperature, the final temperature is the one that we need to record. So from there, read and record the highest record the highest temperature. We shall call this one T3 degrees Celsius attained by the mixture. Attained by the mixture. So we have the initial temperature of sodium hydroxide solution, the final temperature, and now we have the temperature after mixing the two. There is that final temperature when the reaction occurs and heat is given out the surroundings. We have what we call treatment of results. Density of solution is 1 gram. We assume that it's the same as the density of water, 1 gram per cubic centimeter. Specific heat capacity, shall abbreviate it as SHC of solution. We shall call it small letter c as they do in physics. Joules per gram per degree Celsius is the capacity of the solution. Total volume of mixture. Total volume, remember how the V cubic centimeters of sodium hydroxide and V cubic centimeters of hydrochloric acid, and this will give us 2V cubic centimeters of resultant solution. Then mass of mixture, or mass of solution, is equal to the volume times density. So it will be 2V times 1, which is 2V, and this will be grams. Then we have the average initial temperature. This is the temperature of the sodium hydroxide solution plus the temperature of the hydroxide of the hydrochloric acid, all before mixing, divided by 2, and we shall call that initial temperature in degrees Celsius, measured in degrees Celsius. Final temperature, the final temperature after mixing the two solutions, the temperature attained, final temperature, we called it T3 degrees Celsius. So temperature change after the reaction had occurred is equal to final temperature minus initial temperature. And it is T3, the final temperature, minus the initial average degrees Celsius. We shall call it delta T degrees Celsius. So that's the information that we need in order to carry out our calculation. Now we have to calculate the heat absorbed by the solution. So because the reaction occurred and the temperature rose because that rising occurred because the solution had absorbed some heat, and this heat is obtained by multiplying the mass of the solution times the specific heat capacity of the solution times the temperature change or temperature rise. Temperature change. You can call it temperature change, but you can also call it temperature rise. Now the mass of the solution is 2V grams. The specific capacity, heat capacity is said to be equal to delta C, and the temperature change is delta T. So the heat absorbed by the solution is 2V C delta T, and this is heat energy, so the units are joules. Now we also need to know the number of moles of the acid, because this is the number of moles of the acid. These moles of the acids are the ones responsible for producing hydrogen ions, which reacted with hydroxide ions, so that this heat energy is liberated. So we need to calculate the moles of acid used, or number of moles of hydrochloric acid. And this was V cubic centimeters of 1 molar hydrochloric acid. So, being 1 molar means that 1,000 cubic centimeters of solution contain 1 mole of HCl. What about the V cubic centimeters of the same solution? When you cross multiply, they contain 1 times V over 1,000 moles. So the number of moles of the acid is V over 1,000 moles of acids or of hydrogen ions, because hydrochloric acid is monobasic. So these are the moles which liberated this heat energy. The number of moles of hydrochloric acid, or the number of moles of hydrogen ions, according to our experiment, we had the same number of hydrogen ions as hydroxide ions. So you can decide to use moles of hydrogen ions or moles of hydroxide ions because they are the same in number. Now, how do we calculate the enthalpy of neutralization? These moles here liberated this amount of heat. If you can get the number of moles of hydrogen, the heat energy liberated by 1 mole, then we shall be having the enthalpy of neutralization. So V moles, V over 1,000 moles of acid or of hydrogen ions liberated to V C delta T joules. What about 1 mole of hydrogen ions liberates? Here we shall just cross multiply 2V C delta T times 1 over V over 1,000. These are the joules, and on simplifying, we shall have this becomes 2V C delta T over V times 1,000 joules. And if we call this enthalpy, because the energy given out when 1 mole of hydrogen ions reacts, enthalpy of neutralization will be equal to this value, but with a negative sign, because heat energy was given out, so the process is exothermic. When the process is exothermic, the enthalpy change is negative, and this will be joules per per mole. So that's the enthalpy of neutralization in the experiment. Let's now talk about the sources of error. What could be the sources of error in the experiments? Sources of error could be heat losses to the surroundings. E.g., the thermometer itself absorbs some heat. Even the beaker to the thermometer, the beaker. Another source of error could be errors made when measuring masses and volumes during the preparation of the solutions of acid and alkali. That can also be a source of error in the experiment. Now there is a question which we have to answer about the experiment, and we already have this question in our notes which you took. So that means I may not even have to write the question again. I need to save time. So the question reads: in an experiment, 25.0 cubic centimeters of 2 molar monobasic acid at 23.5 degrees Celsius was added to an equal volume of 2 molar sodium hydroxide at 25 degrees Celsius. Temperature of the mixture changes to 36.5 degrees Celsius. They give us the density of the solution as 1 gram per cubic centimeter and the specific capacity of solution as 4.2 joules per gram per degree Celsius. We're going to do that number as follows. In the first question, they're asking us to calculate the number of moles of the monobasic acid. That is part A. Moles of acid. Remember, we had 25 cubic centimeters of 2 molar monobasic acid. 2 molar monobasic acid. So, according to this, you have 1,000 cubic centimeters of acid solution contain 2 moles of acid. What about 25? These ones contain, here I simply cross multiply 2 times 25 out of 1,000. This gives us 0.05 moles of acid. So that is our part A. In part B, they're asking for the heat absorbed by the solution. Part B, Roman 1, heat absorbed by the solution. So we need to have this information and use it. Total volume of mixture equals 25 plus 25, and this gives us 50 cubic centimeters. Then mass of mixture equals volume times density, and this is equal to 50 times 1, which is 50 grams. Then average initial temperature equals 23.5 plus 25.0 divided by 2. So this was the temperature of the acid, and this is the temperature of the alkali. And when you add and divide by 2, you get 24.25 degrees Celsius. Then the final temperature of the mixture. According to our question, it was 36.5 degrees Celsius. So you can now use this to get the temperature change. Temperature change or temperature rise, delta T equals 36.5, the final minus the initial. This on subtraction gives us 12.25 degrees Celsius. From this, you can calculate the heat absorbed by the solution equal to, this will be equal to mass of solution times specific capacity of solution times temperature change. So according to our information, the mass of the solution is 50. The specific capacity of the solution in the question was given as 4.2 joules per gram per degree Celsius, and the temperature change is 12.25. And when you calculate this, you get 2,625 joules. So this is the heat energy which was absorbed. That is part B, Roman 1. Then part B, Roman 2. Part B, Roman 2. They asked for the molar heat of reaction. Remember, in part A, we calculated the number of moles of the acid, and this was 0.05 moles. So 0.05 moles of acid liberated this heat energy of acid liberated 2625 joules. What about 1 mole? 1 mole. Remember, this is a monobasic acid, so these are moles of hydrogen ions. 1 mole of hydrogen ions liberates. Here we just cross mark 2625 times 1 over 0.05 joules. So the amount of heat energy liberated is 52500 joules. So if you call this heat of neutralization or enthalpy of neutralization, or heat of or molar heat of reaction, between acid and sodium hydroxide. Since it's a heat of neutralization, it should be exothermic. The negative sign is necessary to show that heat energy was given out. And if it is heat of neutralization, that's molar heat of neutralization, should have units of joules per mole. So that is it. You can look for more questions about calculating enthalpy of neutralization and try them out. So that's what we have had today, and I hope you have been following very well. I wish you the best in whatever you do. Assalamu alaikum wa rahmatullahi wa barakatuh.